So we were discussing tautologies, which is a propositional expression or a form taking the truth value true always. Then we were discussing something called contradiction. Analogous to this, it's a propositional expression or a form taking the truth value false for all possible values of the proportional variables appearing in the given expression. Suppose for all possible values of the proportional variables we find a mix of true and false, then that's called contingency. So the advantage of things like having an expression which is a tautology or having an expression which is a contradiction and things like this, these things will help us to simplify the expressions given a logical argument. So we saw that P imply Q is equivalent to writing negation P or Q. This also means P imply Q implies negation P or Q, and the converse is also true, which means negation P or Q implies P implies Q. And we also looked at P implies Q and Q implies P is equivalent to saying P biconditional Q. And if P imply Q imply negation P or Q is a tautology, then we write like this. And if single imply, which is conditional expression, is a tautology, then we write using implication. If both A implies B and B implies A are true, then A and B are equivalent, or A biconditional B is a tautology. Okay. So if you look at expressions of this form, say P implies, say P or Q. Okay. So you have an expression involving two proportional variables. Let's look at that. So you have P, you have Q. So it's P or Q. So P or Q is true, 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 false. So P imply P or Q. Okay, so P imply P or Q. So this one is true, this one is true. When premise is false, the statement is true. So this shows that for all possible values of P and Q, the expression is evaluated to true, which means P implies P or Q, or this one is a tautology. Now the question is the converse true? Or the question is P equivalent to P or Q? Equivalently, is P or Q implies P. Suppose if this one is true, which means they both are equivalent. Let's verify that here. So let's look at P or Q implies P. So you have P or Q. Does it imply this? So it's true, false, and true. What is this? This one is a contingency. Neither a tautology nor this one. And is this? Answer is no. Which means this is also no. Is the converse true? Answer is no. So now there are expressions for which you can get only one part, which is, for example, P implies P or Q, but the converse is false. So not all expressions are equivalent. Some expressions are only one way. For example, P implies Q implies this, and some expressions are both negation P or Q implies P imply Q as well. So some expressions you get to see only one way. For example, P imply P or Q, and when we were checking whether the converse is true, it turns out that the converse is false. For many expressions that we come across, only one direction is true and the other direction is false. Not just that, there are expressions for which even the forward direction may not be true. So please verify this, whether P imply Q imply R, is that implying P imply Q imply R. Suppose now there are three variables, so which means 2 power 3, 8 possibilities will be there. And when you verify P imply Q imply R, imply P imply Q imply R, if it turns out that is a tautology, then this is true. Suppose it is not a tautology, you get a contingency like this, which means P imply Q imply R does not imply P imply Q imply R. If this one is a tautology, then this implication is true. If this one is a contingency, then this premise does not imply this conclusion. So you may later verify and check whether this one is a tautology or a contingency. And so we come across all three types of expressions, and some of them are tautology, contingency, contradiction, and some of them you get to see that forward direction is true, we say implication is true. For some of them both forward and the backward direction is true. Such expressions we call it as equivalence. Okay, we will look at some case studies and see how this translates into practice. Let's look at a couple of case studies and see how proportional variables are helping us to simplify the expression and subsequently helping us in proving a given argument. Let's look at this. Dm is a classical subject. So something like it's an argument. You can imagine like a computer scientist is making a sequence of statements of this form. So the first statement that he makes is, he says Dm is a classical subject. Second statement, he says if Dm is a classical subject, then BTech CSE is a good program. Then he concludes. He says, therefore, when he says therefore, which means he is concluding his argument. So therefore, BTech CSE is a good program. So he is making two statements. DM is a classical subject. Then he says if DM is a classical subject, then BTech CSE is a good program to study. Therefore, he concludes. He says, given this premise, he is concluding. Therefore, BTech CSE is a good program. Okay. Now, we want to know whether his argument is valid. Is the above argument valid? What does that mean? Does the conclusion follow from the premise? Does the conclusion, does it follow from the premise? Okay. What we will do is the following. When we discussed proportional variables, we said they are all abstractions. And so with the help of abstraction, proportional variables, we said one can convert an argument, a logical argument, into an abstract representation, and the validity of the argument can be verified using the abstract form, using proportional variables and so on. Fine, this is what we have discussed. We will take that idea now. So DM is a classical subject. Let me call it as P. If DM is a classical subject, then BTech CSE is a good program. BTech CSE is a good program. Let me call it as Q. So what is given? What is given to us is the following. P is given, and we are also given P imply Q, and therefore we want to know Q. So listen, it is a premise or it is an argument implying this. We want to know, how do you formally write? I am making a sequence of statements, or so and so is making a sequence of statements, which means this statement and third statement and so on. So in an argument, if I make sequence of statements, they are all connected using the logical operator AND. Then we want to know therefore. Therefore is precisely whether this one, does this implies Q. Okay, this is our question. This is what we want to know. Given P and P imply Q, does Q follow from this? Equivalently, is P and P imply Q a tautology? If tautology, if the above expression is a tautology, if the above expression is a tautology, then as we discussed before, then Q follows and the claim is true. Correct? I repeat, given an argument of this type, we want to know whether the argument is valid or not. So to talk about the validity of the argument, bring the first level of abstraction by introducing proportional variables. So P represents DM as a classical subject, it's a proposition. If you fix a context and the context of CS people, and we see that this is a proposition, and the other day we were discussing that we come across context sensitive propositions and in practice, and here is one example. And so what is given to us is DM is a classical subject. Please note, if DM is a classical subject, then beta CSE is a good program. Because of if then, I've used conditional operator, and then so and so person is concluding that beta CSE is a good program. Now I wish to know whether Q follows from this. So given argument is always a sequence of statements, which means they are connected by the logical operator and. If I make 10 statements, then the first statement and second statement and third statement and so on up to 10th statement. Then when I say therefore, which means I am concluding my argument, so therefore Q. So we want to know, given this, does this imply Q? Formally, P and P imply Q. Is it a tautology? Suppose it is a tautology, then if this appears, I said before, I can replace this with Q, which means Q follows from this. So now let's verify, is this indeed a tautology? Okay. So what we have is P, Q, taking the value true, 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 false, false, true, false, false. And now we look at P imply Q, which is true, false, true, true. Then we look at this expression P and this, let me call it as W, and P and P imply Q. So P and P imply Q is true, false, false, false. Now I wish to know W imply Q, correct? And this is my W, this is my Q. True, true is true. When premise is false, the statement is true. So it tells you that this expression is a tautology. So what is this telling me? I can conclude Q. So Q follows. So Q follows. The argument is valid. So this is our objective. So given an expression of this type, first convert them, bring in formalism, convert them into an expression involving proportional variables. Then you ask, what is the question trying to address? And often you will come across an argument concluding something. So therefore, take logical and among all statements, that's precisely your premise implies whatever the conclusion the argument is asking for. So simply take that expression and see how many variables are appearing. If there are k variables, p, q, r, s and so on, create a truth table with 2 power k rows and evaluate the expression. If it turns out that for all 2 power k rows, and the last column, which is precisely the expression itself, is evaluated to true, you say the argument follows. And if it turns out that the last column, which is the logical value of the given expression, is not a tautology, which is either a contradiction or a contingency, and that shows that the conclusion is false. Conclusion does not follow from the given premise. And so something like this is what we will come across often in computer science. We will see some more examples and to appreciate uh, the concepts like tautology, contingency, implication, equivalences, and so on. Let's look at this case study. If DM is a classical subject, then BTech CSE is a good program. If BTech CSE is a good program, then MS in CSE is a good program. Therefore, if DM is a classical subject, then MS in CS is a good program. Fine. So, very similar to the way we did the previous example. So, convert this argument into the proportional variables, bring in abstraction. So, let this is say P, and this one is say Q, BTech is Q, and this one is R. So what is given? P implies Q and Q implies R. We are given two expressions. We want to know, therefore, P implies R. Correct? So this is my premise. DM is a classical, if DM is a classical subject, then BTech CSE is a good program. And second statement, if BTech CSE is a good program, then MS in computer science is a good program. This part is done. Then therefore conclusion starts. Conclusion says, if DM is a classical subject, then MS in CS is a good program. So we want to know, is the above argument valid? So can we conclude? P imply R. So does all are equivalent? Does P imply R follow meaning does it follow logically, and from P imply Q and Q imply R. Fine. Let's look at it. So you have P, you have Q, and you have R. And the possible values for this one are, this one is true, false, true, and true, false, false. So there are 3 variables, so we have 8 rows, and this guy, when he is taking true, and Q and R can take possible values true, false, true, true, false, true, false, false. Similarly, when P is taking false, Q and R can take true, false, true, true, false, true, and false, false. Now let's check whether the expression is true. So we need to look at P imply Q, and what is P imply Q? And true, 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 false is false. Now premise is false, so you can straight away write true, true everywhere. Then we need to look at Q imply R. So Q imply R, true, false is false, which is true. Premise is false. True, false is false. Premise is false. Okay. Then let's look at the AND. P imply Q and Q imply R. Correct? What would be that value? That is false, true, false, 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 true, true, true. Then we look at P imply R. So when we look at P imply R, true, false is false, true, true is true, true, true is true, true, false is false, and after that premise is false, so it is true everywhere. So we have seen P imply Q and Q imply R. We also looked at this. Then the last one is, that's precisely what we want. P imply Q and Q imply R imply P imply R. Okay. So we can even call this one as W. This one is Z, which means this one is W imply Z. Correct? So this part is done. Where is our W? W is here. Where is our Z? Z is here. Okay. And now we want to know whether W imply Z is true. And this one is true. This one is true. This one is true. Premise is false. Yes. Now this one is a tautology. This one is a tautology, which means conclusion follows. The above argument is valid. Can we conclude? Yes. Answer is yes to all of them. So I can say P imply Q and Q imply R logically implies P implies R. So what is that we have done? An argument of this type, represent them using propositional variables and identify what is the premise and what is the conclusion, and then switch to truth table and look at all possible values of propositional variables, and if the expression is evaluated to true, then it becomes, which means then the expression is a tautology. We can say conclusion follows, or P imply Q and Q imply R implies this. If you read this on the face of it, it appears like they are not related, but through this logic, it turns out that they are related. Not just that, so and so follows from the given argument. They are related, and one can make a meaningful conclusion following this logic. And that is the focus of this course. In a logical conversation involving statements of this form, you suddenly see that in the argument a person is making a statement which is an inference which follows from the previous statements, and we want to quickly infer and say whether it is true, whether so and so person is making a proper conclusion or not. And for that, the abstraction and the tools that we have learned so far will help us. And we will see some more examples and how it is used in practice, and a couple of more expressions of this form, and involving 2 or 3 variables but other operators, which we shall see now.